We now know that the force is rho g AD. Rho is the mass density, g is the gravity, d is the depth, and a is the area of the slice. The area is the width times the thickness. In this formula, the depth varies depending on how far below the water level the slice is. We then set up the Riemann sum to obtain the definite integral. The force is the integral of rho g are constant, times the depth times the width, the thickness is dy. Oftentimes, in a thin vertical plate, the width of the slice depends on how far below the water level the slice is. For example, in this figure, the width is longer for the slices near the surface of the water. Thus, the width is a function of y. If we were to position y equals 0 at the water level, the depth of the slice below the water level is yi. The width is therefore a function of y. We call this L. The force on the slice is rho g dA, where d is the depth yi and a is the area of the slice, the width L of yi times the thickness delta y. Notice that L of yi times delta y is the area of the slice and depends on how far below the water level is. The widths vary. The depth is the distance from the slice to the water level. Rho and g are constant. Keep in mind that if we were to use the customary system, then rho g is delta. The total force is the sum of rho g yi, L of yi, delta y at I go from 1 to n. And at n go to infinity, this Riemann sum will give us the definite integral. Rho g are constant, so we can move rho g in front of the integral sign. If this is the US customary system, then the force is delta, the integral from a to b, y, L of y dy, where L of y is the horizontal width of the slice. Delta is the weight density. For example, a vertical plate is submerged, partially submerged in water. With the shape, approximate the hydrostatic force against one side using the Riemann sum, then set up the integral and evaluate it. The thin plate is partially submerged in water. We only find the hydrostatic force for the part that is submerged in water. We need to slice the thin plate horizontally so that any point on the slice has the same depth from the water level. We then position the coordinate axis so that y equals 0 is at the water level with the positive direction pointing down. The depth of the slice is yi. The force on this slice is rho g AD. Rho g are constant, d is the depth, a is the area of the slice. The depth is yi and the area is the width times the thickness, but the thickness is delta y. Note that the width of the slice depends on how far below the water level the slice is. And so the width is the function of y. There is a linear relationship between the width and the depth. When the depth is -1, the width of the slice is 4 on the top, and when the depth is 1, the width is 2 at the bottom of the trapezoid shape. The width is a function of y W equals L of y, where this relationship is linear because the side is a straight line, whose slope is 2 minus 4 over 1 minus negative 1, which is minus 2 over 2 or negative 1. We can also see that the initial width when y equals 0 is 3, or we can use the slope-intercept form. W equals minus 1y plus b. Plug in 1 for y and 2 for w. We have b equals 3. And so the width is L of y equals minus 1y plus 3, or 3 minus y. The width L is a function of y. That the force on the slice is rho g yi. The width is now 3 minus yi, and the thickness is delta y. This is the force on one slice only. The total force is the sum of the forces on all of the slices. We add these up from I, go from 1 to n, rho g yi, 3 minus yi, delta y. There are n slices. As n goes to infinity, we obtain the definite integral. We add up the slices from y equals 0 to y equals 1 only. Rho is 1000, g 9.8, yi is now y, and 3 minus yi is 3 minus y. Delta y becomes dy. For the limit of integration, the lower is 0 and the upper is 1. We simplify this definite integral. 9.8 times 1000 is 9800, which is a constant, so we move it to the front. Evaluate this integral. We will get 11,433.33. The unit is newtons. Another example. This time, it is in the U.S. customary system because feet are given. The thin plate is fully submerged in water, so we position the coordinate axis so that 0 is at the water level still. We slice the thin plate horizontally. The depth of the slice is yi, as before. The thickness is delta y. Thus, the force on this slice is now the weight density times the depth times the area, which is delta dA. Notice that rho g is being replaced by delta because the units are in feet. The depth is yi, and the area of the slice is the width L of yi times delta y. It remains to find an expression for L of yi, but we notice that the width is twice the horizontal leg of this right triangle. This horizontal leg is half of the width. The vertical distance is 7 minus yi. The radius is 5. In this right triangle, the vertical leg is now 7 minus yi. The hypotenuse of this right triangle is the radius of the circle, which is 5. And using the Pythagorean theorems, we have x squared equals 5 squared minus 7 minus y, the quantity squared, which is x squared equals 25 minus 7 minus y squared. So x is the square root of 25 minus 7 minus y, the quantity squared. This x is half of the width, and so the width is 2 times the square root of 25 minus 7 minus y, the quantity squared. Thus, the force on the slice is delta, which is the weight density. The height is yi. The width is now 2 times the square root of 25 minus, open parenthesis, 7 minus y, close parenthesis, squared, times the thickness, which is delta y. The total force is the sum of the forces on n slices, the sum as I go from 1 to n of 2 delta yi, the square root of 25 minus 7 minus y, the quantity squared, delta y. This is the Riemann sum for the total force. As n go to infinity, we obtain the definite integral. 2 delta is a constant, so we move it to the front of the integral sign. Y times the square root of 25 minus 7 minus y, quantity squared, dy. For the limits of integrations, we add up the slices on the thin plate only, so the lower limit of integration is 2 and the upper limit of integration is 7. Evaluate this definite integral to obtain approximately 11,972.25. The unit is pounds. In this computation, we use the weight density of water, 62.5 pounds per cubic feet. But if we were asked to use 62.4 pounds per cubic foot, the answer might be slightly different.